Hello everyone, I'm Pietro Sala, and today I'm talking about on a temporal logic of prefixes and infixes, which is a work with Laura Bozzelli, Angelo Montanari, and Adriano Peron. So we all know regular expression. We have that a regular expression is represents a set of finite words that can be the empty set, the empty word, a word which is composed by exactly one symbol, a word which is an iteration of the finite iteration of the words in a given language, or the union of two words in a regular language, or the concatenation of two words taken from two regular languages. Okay, so if we remove we disallow the use of the star iteration, we obtain star-free regular expressions, which are in this form very limited, because if you think about how the classical automata construction for regular expression, and you apply to this fragment of them, you have that basically you are disallowing the ability of introducing loops, because loops are introduced by means of the star operator. When you compositionally build the automata, you introduce loop only when you have a star operator. So basically, this language, this class of languages, basically can encode just the finite ones. And for instance, star-free, sorry, sigma star is not a star-free regular languages. We recover this. It is possible to recover this problem and make the languages very interesting by introducing the negation. So instead, by completing what is the logical part of the regular expression, which has already the plus, which is the union, which is the equivalent of the OR operator, the logical OR operator. You introduce negation with basically the language of the negation of E is the set of words that doesn't belong to the language of E. And let us observe, for instance, that sigma star is equal to the negation of the empty set. Introducing negation, while it's very easy to see if a language is not empty for star-free regular expression, it's not as simple for generalized star-free regular expression. As a matter of fact, it's it becomes an exponential, non-elementary hard problem, which means that you have a tower of exponential which is bounded by the size of the original expression. So this is a classical result by Stockmeyer. You will find it usually into star-free regular expression equivalence in its original formulation, but the very same result applies to the emptiness of the language, to the emptiness problem of the language. So let us focus on the fact that we want to retain the logical structure of the full logical structure of the regular expression. So we want the plus, aka the disjunction, and the negation, but we want in some way have a better complexity. See which fragment of this generalized or free regular expression have a better complexity. So the so we have to focus on introduce restriction on the concatenation operation. As a matter of fact, if you look at the proof of Stockmeyer, the tower, basically the exponential tower, is given by the alternation of concatenation and negation. Okay, so once you alternate concatenation and negation, you have that this tower of exponential builds up. So why don't we replace the concatenation with a combination of unary operations, which are a weaker version of it, like prefix, suffix, and infix operation. So we have the prefix operator, which says that the language of the prefix of E is all the words for which E which have a prefix, a proper prefix. Here is less than, okay, a proper prefix of the in the language of E, and this may be represented with this use of the concatenation operation. You have to concatenate E with the star, sigma star, and sigma, so you have a proper prefix. So we are using the concatenation just in this form, by concatenating. If you use prefix, we are just concatenating to the right sigma star and sigma. Okay? While we will use the suffix operator, which is the language, all the words that has a suffix in a given language, we are just using the concatenation by concatenating sigma star and sigma to E. Okay? But we allow negation. Okay? And the infix, which is a combination of the two, that says that a word belongs to the language of the infixes of E if it has such word has an infix, a word which is strictly contained in the current one, which belongs to the language of E. And here is another way of constraining, maybe seen as another way of constraining concatenation, and say, okay, we can only concatenate with the two arbitrary words on both, non-empty arbitrary words on both sides. Obviously, it's easy to see that the infix operator is maybe seen as a combination of prefixes and suffixes. So here we have all the possible restrictions of generalized star-free regular expression according to these three operators, provided that prefix and suffix entails the infix relations. Basically, from the point of view of complexity, we have that these are the four problems, because prefix and suffix have the same complexity, and also their combination with the infix operator. So let us move to the logical part of the talk, and we want to start to talk about homogeneous interval models, which are models, propositional models, which are finite. They have a bound n, and a valuation function that maps such point over this finite linear order to a subset of propositional letter, like in classical LTL models and so on. And for example, here we have the model with 7 points and the letters P and Q, the matrix that identifies which point contains P and which point contains Q. So here is the model, and from this model we extract, okay, this is the key property of homogeneous models, a function over the intervals that maps interval to subset of propositional letters. How we do that? We take an interval and we say that and a letter P, and we say that a letter P holds over any interval if and only if the letters holds over all the points contained in the interval. So for instance, here we have the P and Q both holds on the points contained in 1, 2 and 4, 6. P holds over all the points contained in 0, 2, and Q holds on all the points contained in 4, 7. But the presence of the negation of Q in 0 basically forces us to put non-Q on the interval 0, 2, and the presence of the negation of P on 7 forces us to put the negation of P on the interval 4, 7. And we can basically label all the possible intervals of the model using this definition. If the letter belongs to all the points in the interval, then it belongs to the interval. Otherwise, it doesn't belong. For instance, it suffices this point inside this big interval to forces the violation of P and Q on 1, 6 and 0, 3, for instance. Let us notice that once you have defined the sets of propositional letters over the points, the function over the intervals is uniquely determined. This is the main difference with respect to general interval models, which are given in a similar fashion, but here the function vi is given in the model, is not inferred by the points, and it is completely free. It doesn't depend anymore on the labeling on the points of the interval contained in the current one. So for instance, there may be a model which partially respects the homogeneity assumption. So for instance, 1, 2 is homogeneous, 0, 2 is homogeneous, 0, 3 is homogeneous. And you can also have points which doesn't respect the homogeneity assumption. For instance, if you put 0, 0, 6, this is not an homogeneous model, it's a general model, because you put, for instance, P and Q over 1, 6, where you have the negation of P and the negation of Q inside the interval, and for instance you have that you put the negation of P and the negation of Q over 4, 6, which is an interval that with points contains both P and Q. So in general interval model you are completely free to label the intervals. So homogeneous models may be seen as a semantic restriction of general interval models. And as we will see, if we restrict ourselves on homogeneous interval models, we have that many interval-based logic turns out to be decidable. And one of them is the CHOP interval temporal logic, which is formulas are generated by this grammar. You may have and P, the constants pi, the negation, disjunction, and the modal operator CHOP, which is the only modal operator in this interval logic. The semantics is given over interval models. You have that an interval models pi if and only if pi belongs to its labeling, and an interval models pi, the constant pi, if and only if the interval is a point interval. So basically pi holds over n, over the point, but it doesn't hold over n prime if n prime is greater than n. Then you have the negation formula. The negation of formula holds over an interval over if and only if the interval doesn't model the formula. The disjunction, that a formula psi1 or psi2 holds over an interval if psi1 holds over such interval, or psi2 holds over such interval. And finally, the modal operator CHOP, that says that a formula psi1 C psi2 holds over an interval if there exists a way to split, you have to find a point between the 2 points of the interval, in which the formula for which the formula psi1 holds on the first part of the interval, and psi2 holds on the second part of the interval. So you have to find a point n second for which psi1 holds over n second, and psi2 holds over n second and prime. Also, you may have the extreme cases that in which you take the first, you chop at the beginning, you make psi1 holds over the point, and psi2 holds over the interval, and the other case with psi2 holds at the end, and psi1 holds over all the interval. And also you have the degenerate case in which you have that everything holds over the interval if it is a point, so you have the psi1, psi2 is holds together with psi1 chop psi2, and you can tell these cases apart by means of the constants pi. So this is why the constants is in the language using this such strict reflexive semantics that you can say, okay, for instance, this is the formula psi1 and the negation of pi, in which you forces the interval to be chopped exactly in between. So you force the first case, the most intuitive one, in which you take which you have a non point interval, so and prime is greater than n, and you chop inside the interval. So we use VI, but there is a great difference if we use general or homogeneous models with respect to the chop logic. On general interval models, the logic is undecidable. You can easily encode the reachability problem for two counter Minsky machine, and so the satisfiability problem is undecidable. For homogeneous models, so if you restrict the class of models to the homogeneous one, the chop logic is exact equivalent to the generalized star-free regular expression, which means that given a generalized star-free regular expression, you can always write a chop formula, an homogeneous chop formula, which if you read the evaluation of the letter over and you concatenate over the model, all the models for such formulas are also words of the language of E, and you can capture all of them, all and only all the words in the language of E. This the reduction from expression to formula may be in logarithmic space, and the opposite can be in linear space. So, but it doesn't it's not a problem, since in this case the emptiness problem for this for a generalized star-free regular expression is a tower of exponential. So from this we have that the satisfiability of chop over homogeneous models is non-elementary complete, and as we did for the generalized regular expression, we relax the modal operator in order, and what we want is to find tractable fragments of the chop logic over homogeneous models, or decidable fragments over the general one. And basically the chop may capture a lot of the HS operator, which are the unary modal operator between intervals that basically subsume the Allen relation. In particular, we are interested in the begins, which we have that basically this is the translation of the begins operator into the chop semantic, and we have that begins psi also over an interval. It exists a proper prefix of the current interval, where psi holds. So this is the extreme case in which the psi holds exactly on the first point of the interval, but the general case is that psi holds over a proper prefix of the current one. Same as for the E, which is the finishes operator. It says that E of psi holds over an interval if there exists a suffix of the current interval where psi holds. This is the extreme case in which we have exactly the psi holds exactly on the end, at the end of the current interval. The more general is when you take a point in between and you make psi hold on the right hand part. And obviously the during with interval operation, for which a formula d of psi holds over an interval if and only if there exist exactly 2 points, okay, where inside the current interval where psi holds. So this is the extreme case in which psi holds in a point inside the interval, but there is the most general one in which psi holds on a proper interval, a non-point interval, inside the current one. Okay, and all these three operators, as we see, may be expressed using the chop operator. And also we have that D may be expressed as a combination of A and B. So if we consider general models, all the interesting combination of these three HS operators are undecidable. So we have that the only decidable logics are begins and finishes considered alone, but they are not so interesting. While if we consider homogeneous interval models, we know that they are decidable. It comes from the chop, from the decidability of chop over homogeneous interval models. So the point here is the complexity. So the point here is find what is elementary and what's not. And as we did for generalized-free regular expression, we can make a mapping between the restriction on the regular expression and the combination of HS operators. So the prefix and suffix became the B and the E, the infix became the D, and with the respective combination. So we have that these generalized free regular expressions are equivalent to this fragment of HS. And what is the state of the art with respect to complexity on homogeneous interval model is that the prefix and the suffix considered alone are NP completed, doesn't change with respect to the general case. The infix is p-space complete, so it's elementary, so having D alone means that it is p-space complete. Until now, the combination of prefix and infix, as well as the combination of suffix and infix, has a complexity with the bounds on the complexity is between p-space, which comes from D, and non-elementary, which comes from chop, and we have this paper that says that the complexity of BE is X-space hard, but as we have from the PD, we have that the complexity, the upper bound to the complexity is the complexity of the chop. In this paper, we proved that the complexity of BD, so is p-space, is between p-space and x-space. That is, we provided an x-space decision procedure from the logic BD interpreted over homogeneous interval models. It remains open the exact complexity, which is now between p-space and x-space, and the most interesting problem of the complexity of the BE, the most general fragment, which also entails the complexity of the prefix and suffix relation for generalized star-free regular expression. And with that, I want to conclude my talk and to thank you for your attention.